When you are developing on a microcontroller, that tiny but powerful brain inside a countless devices around us, one of the very first and most crucial decisions you face is what's going to be the fundamental software layer. Are you going bare metal or are you going to use an RTOS? This is just a technical detail. It shapes your entire project's architecture, complexity, testability, and even its real-time behavior. Hi, I'm Sarana Pandian, CEO of MBN Technologies. For over 23 years, our team and I have built embedded systems across nearly every industry imaginable, from simple consumer gadgets to complex industrial and medical devices. And we have debated the bare metal versus RTOS choice many times. There is no single right answer that fits every project, but there is a way to systematically evaluate your needs and make the best choice for your specific situation. In this video, we will break down the two main approaches and look at a framework for designing the right choice. Bare metal systems. Let's start with the bare metal. This is arguably the simplest approach conceptually. You write code that interacts directly with the microcontroller's hardware, registers, and peripherals. There is no underlying operating system abstracting things for you. Your program often runs on a single main loop, possibly handling external events via interrupts. In this approach, you have maximum control over the hardware. You know exactly what's happening at every clock cycle. It offers the smallest possible memory footprint because you are only including the code you absolutely need. For very simple single-task applications, it can be the fastest and most efficient approach. Development setup can also be straightforward: compiler, linker, and debugger. Managing complexity can be very difficult as your application grows. If you need to handle multiple unrelated tasks concurrently, for example, reading a sensor, updating a display, processing incoming communication data, and managing a motor, you often end up with complex state machines, flags, and timing issues in your main loop, or ISRs. This makes code harder to write, debug, test, and maintain. Real-time guarantees for multiple concurrent events can be hard to achieve or prove. It's also less modular and harder to reuse code across different hardware. It is also less modular and harder to reuse code across different hardware. It is best suited for extremely resource-constrained devices, very simple single-function devices, proof-of-concept prototypes where you need direct hardware access quickly. RTOS. Now let's look at the RTOS, the real-time operating system approach. An RTOS provides a layer of abstraction on top of hardware. Its core job is to manage multiple independent tasks or threads and decide which task gets to use the CPU at any given moment. This is called scheduling. It also provides mechanisms for tasks to communicate and synchronize with each other using interprocess communication techniques such as queues, semaphores, mutexes. These IPC mechanisms can be used to safely exchange data or signal events between the tasks. Here, the structured multitasking makes managing complex applications much more traceable. Each task can focus on its specific job. The scheduler helps provide real-time guarantees for critical tasks. RTOSs promote modularity, making code easier to test and reuse. They also provide a foundation for using complex middleware like networking stacks, file systems, or USB drivers, which are often provided as RTOS-aware components. This significantly improves scalability for larger, more feature-rich applications. An RTOS adds overhead. It consumes some amount of RAM and flash for the kernel and its data structures. There is a learning curve to understand task management, scheduling, and IPC, and pitfalls like priority inversion or deadlocks need to be avoided. The initial setup can take a bit longer than writing a simple main loop. It is best suited for applications requiring concurrent execution of multiple tasks, strict timing deadlines, complex interactions between different system components, projects that are likely to grow in complexity, and those needing standard middleware components. Popular RTOS options. With RTOS, there are many excellent options, each with different strengths, licensing, and ecosystems. Free RTOS. Now managed by Amazon, this is a hugely popular open source portable RTOS that is relatively simple to get started with. It has a great community support. Azure RTOS. A robust RTOS, now part of Microsoft Azure, often pre-integrated or well supported on many MCU families. Zephyr project. An open source scalable RTOS designed for resource-constrained devices supported by the Linux Foundation. microcontroller, another established RTOS known for its reliability and available safety certifications. VxWorks, a long-standing high-performance commercial RTOS often used in demanding industrial, aerospace, and defense applications. Each of these has its own nuances, licensing models, and associated middleware. Your hardware choice might also influence which RTOS is best supported. So, how do you decide between bare metal and RTOS for your project? Over 2 decades, we have refined the criteria we use. It's not about choosing the most powerful or smallest solution in isolation, but the one that is best fit across several dimensions. Let us get into the framework criteria. First criteria, real-time requirements. Does your system have hard real-time deadlines? Or is it soft real-time? Bare metal can do simple real-time in ISR, but for complex interacting real-time tasks, an RTOS with a preemptive scheduler is usually necessary to guarantee response times. Second criteria, task complexity and concurrency. How many independent operations need to run? Do they need to interact or share data? If you have more than 2 or 3 loosely coupled activities, trying to manage them in a single bare metal loop quickly becomes a spaghetti code. An RTOS is designed for this by breaking functionality into distinct tasks. Third criteria, resource constraints. How much RAM and flash does your target MCU have? If you are down to a few kilobytes of RAM, bare metal might be your only option, as even the smallest RTOS kernels have memory overhead. However, modern MCUs often have enough resources to comfortably run an RTOS kernel and several tasks. Fourth criteria, system complexity and scalability. Is this a one-off simple device, or is it part of a larger product family that will grow in features? Is the software likely to become more complex over time? RTOS-based systems are inherently more modular and easier to scale by adding new tasks. Refactoring a complex bare metal system later is often much harder. Fifth criteria, development effort and team expertise. What is your team's experience level? Are they familiar with RTOS concepts? While there is an initial learning curve with an RTOS, for example, complex projects, the structured environment can actually reduce overall development time and make it easier to bring new members up to the speed compared to deciphering intricate bare metal state machines. Consider the availability of middleware for the chosen platform. Sixth criteria, modularity and testability. Can you develop and test individual pieces of functionality independently? In an RTOS, tasks provide natural boundaries for modular development and unit testing. Testing complex interactions in bare metal often requires full systems. Seventh criteria, security needs. While not exclusive to RTOS, some modern RTOSs offer built-in security features, memory protections, or have certified versions for high security applications which can be harder to implement from scratch on bare metal. After 23 years, I can tell you that this decision isn't always black and white. Sometimes a project starts bare metal and evolves to need a simple scheduler or a tiny RTOS. Consider the long-term maintenance burden. What seems faster to code now in bare metal can become a legacy nightmare. The quality of the RTOS port and available drivers for your specific MCU is critical. A poorly supported RTOS can be worse than a well-written bare metal code. Don't be afraid to prototype. Try implementing a key piece of functionality using both approaches on a development board if you are truly unsure. In summary, the choice between bare metal and an RTOS for your MCU project is foundational. Bare metal offers simplicity and minimal overhead for the simplest cases. An RTOS provides powerful, structured environment essential for managing complexity, achieving real-time performance in concurrent systems, and improving scalability. By systematically evaluating your project against criteria like real-time needs, task complexity, resource constraints, scalability goals, and team expertise, you can confidently choose the software foundation that is truly best suited for success. I hope this framework helps you navigate the choices for your next embedded project. If you found this video valuable, please give it a thumbs up. It really helps the channel. And for more insights into embedded systems development from our experienced team, visit our website at mbn.com. Request a free evaluation through the link given in the description below. Thanks a lot for watching, everyone. Until next time, happy embedding.